Hey kids, gals and ghouls. Today we're gonna talk about the camera. So last time we did projection. So we did a perspective and orthographical projection, and I thought it was pretty cool. Thought it was pretty neat, pretty neato. Okay, no. So what do we got? There we go. Our nice little cool depth projected little boy. So I was talking last time that right now we have a setup something like this. Hold on, I'm just gonna move my tea here. I've spiced it with the tears of game assembly students today, so it's a little bit salty, but that's okay. The setup we had last time was something like this. Excuse me while I fetch my drawing pad. There's so much shit over here. I'm so organized. Let me just move this. I'm sorry for screaming. Okay. So we had the camera here at the origin. And we had this cone here projecting outwards, looking at our little plane here, spinning around. So that was the setup we had before. And I was saying that we had to move the little plane outwards from the origin for it to actually be seen, right? Because we had the near clipping plane there. But why didn't we just move the camera? I mean, at some point we're going to have to move the camera, right? Well, so OpenGL doesn't really have a concept of, a camera or anything. It can only do transformations. It can transform vertices, and that's really all it can do. So just like there really is no depth, there really is no projection, or perspective, I should say, the perspective matrix transforms the vertices in our scene to appear like they have depth, or they appear to have perspective. And just the same way, we can transform all the vertices in our world to appear like there's a camera moving around in space and rotating. So how do we do that? Well, if this pen is our plane, and I am the camera looking at it, what happens if I move to the right? So I translate to the right? So I'm gonna move to the right. And what happens is that everything moves to the left, right? But from my point of view, as I move to the right, it appears like everything is moving to the left. Like the whole scene, everything uniformly moving to the left by the same amount. And the same thing if I move to the left, everything in the scene, like all the vertices in my room and so on, are moving to the right. They're moving sort of inversely to how I am moving. So we could get the same effect if I just fix my head in place, and instead of me moving back and forth, I actually move the whole room back and forth. That would look the same as if I'm the one moving. So that's what we will do. We will do a transformation on every single vertex in the whole world. The same transformation. So when we move the camera back and forth, what we're actually doing on every single mesh, we're moving them left and right, like inverse to how we want our camera to move. And that will make it appear as if there's a camera moving around, but really we're moving, if something was off screen here. Right? If we move the camera down to look at this new little plane over here, what we're actually doing is moving everything up. So this will move up out of frame, and then this will come in and take its place here. So now we'll be looking at this object, even though the camera has not moved. Or the camera, in quotation marks. And same thing with rotations, right? If I rotate my head, it's kind of like the whole world is rotating around my head as a pivot point. Right? So everything stays the same distance apart from my head. Nothing moves back and forth or right or left. it only pivots around my head. And the same thing there. We can just take the whole world and just rotate it around the camera. So we use the camera as sort of a pivot point. And same thing, if I rotate the camera or my head to the left, everything seems to rotate to the right around me, right? So inversely to how I rotate my head, we can rotate the world and get the exact same effect. And that's what we're gonna do. So instead of, if we have this, object here that we want to look at, instead of rotating the camera downwards like this, to have the camera, look this way and then the cone will be going like that. Instead, what we're gonna do is rotate each object around the pivot around the camera. So this will move over here and out of frame, and then this will move up and into frame and taking that plane's place. So again, we'll get the desired effect. It will look like there's a camera sort of capturing stuff and moving around and rotating, but actually we're just transforming all of the vertices to look like there's a camera. Which means that if we have a shader that doesn't do this, like for example, if we have this coffee mug, I forget or whatever to do that transformation, it will just be stuck on screen as I'm moving and moving my head around and rotating, because it doesn't know that there is any camera. It doesn't know that we're doing any of this stuff. By default, it's just gonna be there, and that's just what it's gonna do. So it will be stuck on screen and ruining that illusion. So that's the illusion of the camera. And in 3D graphics, this is called the view matrix or the view transform. We had the model matrix, which was how are objects arranged in the world, position, rotation, scale. We had projection, how are things projected onto the screen, do we have depth, do we have orthographic, and what's the aspect ratio of the screen and so on. And then we have view, which is how is the camera positioned. And these are the three matrices that make up 3D graphics mathematics. So we call them the model, view, projection. So let's do it. Let's make a view matrix. And so I'm gonna make a mat for view here. And we're gonna use a function called look at. And this is one way of doing it. Like there's many ways to do camera view matrices, but one very useful one is called a look at matrix. So here we have three variables, or three arguments, I should say. We have the eye, we have the center, and we have the up. And the way this works is that this will set up a camera matrix that has position I, so that's where we put the camera, that's the position of the camera. We have the center position, and that's where it will look. It will look at the center. So the center position will be in the middle of the screen. It will be completely trained on the center. And then the up is what's up. I never said that out loud. Oh, that's so dumb. Yeah, it will define the up vector. Because while it might be obvious to us about when we're working in Unreal or something, what's said is obviously the up vector or whatever. In OpenGL, that's not defined. There's no defined hard up vector. We can put the up vector whatever we want. So it will sort of define it. Okay, I'm standing here, I'm looking at it, and up vector will define how I'm tilted like this. So I will still be in the same position, looking at the same object, but it will define where I point the top of the camera. It won't be exact, like the top won't point exactly to the z-axis, but it will be, it will define sort of a pitch plane, if you will, I guess. So if when I pitch up and down like this, it will define that plane with the up vector. So the up and the forward vector, I should say. So let's do I. So let's put it. I have no idea really. Let's put it at, I guess, I don't know. Let's put it at like. Let's make it go back and forth. Like it's nothing interesting is gonna happen if we don't do that. So I'm actually gonna make it go back and forth on the x-axis. So that should be right to left. and then 0, 0 for the other two. Then center. So I will have it actually look at. I'm gonna put it a bit away on the Z axis. I'm not gonna put it to Z axis. That's out of the screen. So it's gonna be 2 units out of the screen. And I will have it look like straight in the middle, right in the origin. That's where I want the camera to look. And then the up vector, I'm gonna do the y-axis, because that's what we've kind of been working with so far. And you apply the view matrix just like we did with the projection matrix, but we want to do it before doing the projection. We want to move everything into frame, so you know what's in the center is in the center, what's to the sides are to the sides. And then we want to apply projection to that view, all right? So we want to view right there. Okay, so it's applied. For instance, it goes from right to left. Now we're doing scaling, rotation, translation. Then we're moving the camera, and then we're applying projection to that. So let's see what happens. Okay, so you can see it moving back and forth for sure, but it is kind of hard to see what's happening. So I'm actually gonna move it to the center again, because we moved it away before. So I'm gonna move it back, because now we can simply just move the camera back instead of having to push the thing away. I'm gonna actually make it stop rotating for just a little bit. So I'm actually gonna do ×0 here just to make it stop. Just to stand still so we can see clearly what the camera is doing. And there we go. So now we can see the plane is still, it's completely stationary, but the camera's moving back and forth, so we're still, you know, seeing sort of a different angle of the object. And you can see it's sort of growing and shrinking a little bit, like it's getting a little bigger, and then there it goes, getting a little smaller. And that's just because the camera is moving further away, like it's 2 units away on the Z-axis out from the screen, and then it's moving back and forth like this, which will mean like I will go a little bit further away from you when I'm to the sides, and I'm gonna be closest when I'm dead in the center looking straight at you. So that's why it's sort of, you know, growing and shrinking a little bit. Let's make it a little bit more, make a bit more dynamic camera angle. So I'm gonna do let's do X position is gonna be sine of time, and then I'm gonna make the Z the cosine of time, so it will go in a circle in the X and Y coordinates, and then I'm gonna put it up on the Y by 1, and then I'm gonna actually multiply that by 2. And then still looking at the origin, and now we should be spinning around a little bit, hovered over the thing. So let's see what happens. Yeah, there we go. So now you can see it's stationary, like the model itself is completely stationary, but the camera is circling around above it like this, looking down at it. Very cool. Yeah. I'm wondering if we actually should draw another guy under him, just to sort of make a ground per se. Let's do that actually. So I'm gonna copy, let's see, let's move the time up here. And I am gonna copy, let's move this up there. And I am gonna copy all of this. So I'm gonna draw standing man. I'm gonna copy it, and I'm gonna do draw ground man. So I am gonna move him downwards a little bit. So I'm gonna move him down by 0.5 in the Y axis, moving him down. Scaling, no, it's scaling by 1.5. Yeah, sure, why not? And then I'm gonna rotate him 90 degrees just to sort of make him flat instead of standing upright. So I'm gonna radiance 90 degrees, and then I'm gonna rotate around, not the Y-axis, let's do the X-axis. Yeah, that'll be fine. And then let's see what happens. Oh, whoops, let's get rid of this. Uh-oh. Uh-oh. we're going too far. Okay, so what happened here is that there is no sense of what's ahead and what's behind by default in OpenGL. When you start up a new project, there's not going to be any what's called depth testing, like seeing that, okay, these pixels being drawn on the standing up guy, they are ahead of the pixels being drawn by the ground guy, because he is that below him. And that gets fixed by something called depth testing. But I don't want to go way too off topic, so I'm actually going to just move the draw man, because what's happening is we're first drawing the upright guy and then the ground, which means the ground actually goes on top of the pixels of the standing up guy, even though they are generally further away. So it's the order of when you draw things that, you know, things actually appear on top. So I'm just going to move the ground, since I know that's, you know, almost always behind the dude. I'm just going to make that, draw that first. I don't know. Now these get reversed. Whoops. I'm just going to move them up. Oh, excuse me. Like so. So now, okay, there we go. So now that was fixed. Sorry about that. I didn't think about that. There will be a video. Next video, actually, I think, will be about depth testing. Yeah. So now we can clearly see, okay, the ground is a better reference point for how are things actually rotating here. We can actually make the camera also move a bit up and down. So if we do this, like the sine of time times 0.2 or something, now we should go like above and below it. And let's make it a little bit less extreme. Let's actually do 1 plus this. Like so. So we're still 1 unit above and then hovering up and down a little bit. That was too slow. Let's do 1.67. Yeah. Hopefully that's not too fast. Yeah, okay, there we go. So now you can see the camera's also moving upwards and downwards a little bit. Still focused on this guy. All right, so there we go. So that's the view matrix, and now we have projection and view. I usually clamp these together into one like camera concept, right? This camera has a concept of where it is, and also, you know, it's orthographic or what's the field of view and stuff like that. Because if you're working in an engine like Unreal or Unity, settings like, you know, field of view and stuff like that is usually on the camera. So I usually group these two together as like the camera matrix. Then we have the model matrix here, which is, you know, scale, rotation, and translation. Cool. So that's all of the transformations that we're gonna talk about this course. I think we might do one more or something like that. But now we have a few corners of what can transformation actually do, what is it used for, and so on. We don't have the whole picture, of course, but because it's such a huge concept. But we have a few of the corners, and you know, we have some surface level knowledge. So next time we might do some cleanup. We might do depth testing. We'll see what I feel is most important for next lesson. But until then, have a great day.